Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. Whether at work, in our research, or at home, we often are interested to tell people about how soft or loud a sound is. In this video, we'll learn about sound levels, which help us compare the loudness and energies of acoustic waves.
So let's get started. Well, first by summarizing our sound quantities that we'll often use in acoustics. Acoustic pressure is our first. The complex acoustic pressure is equal to the complex amplitude A divided by R multiplied by e to the j omega t minus kr. This is of course for spherical waves, yet this is one of the most common forms of acoustic waves in many engineering practices. The acoustic intensity is equal to the RMS squared pressure divided by rho naught C. And finally, we have acoustic power, which is the intensity multiplied by some area around the acoustic source. So to create a level quantity that helps us characterize pressure, intensity, and power, we first must recognize that day-to-day acoustic pressure amplitudes vary by orders of magnitude. This table really makes that point. We have a column of sources on the left and a column of the corresponding acoustic pressures on the right in terms of RMS pascals. So normal conversations day to day occur at around 5 millipascal, also written as 5 millipascal. Whereas instantaneous hearing loss is 20 pascals. Going to the far extreme, rifle fire is somewhere around 7,000 pascals, which incidentally is not much more than the acoustic pressure for a balloon popping. So what we see here very clearly, and the way in which the numbers are presented makes this emphasis, we see many orders of magnitude varying, even from hearing loss down to the threshold of hearing, which is 20 micropascals. So in order to capture and help people understand this range of acoustic energies and pressures, we need a logarithmic metric or level to help quantify this large range. And that is provided by the sound pressure level, or called SPL. It uses a decibel or dB scale to quantify the amplitudes of acoustic pressure. The sound pressure level SPL is equal to 20 times log base 10 of the RMS acoustic pressure divided by a reference acoustic pressure. So for air, the reference acoustic pressure is 20 micropascals, whereas for water, such as in medical ultrasonics, the reference acoustic pressure is 1 micropascal. So how do we contrast SPL or decibel values of sound level with respect to the pressure amplitude? So let's create a table of pressure amp change and SPL change. So if the pressure amplitude is changing by a scalar of 1, there is 0 dB SPL change. If the pressure amplitude doubles, this is equal to a plus 6 dB change. Conversely, if the pressure amplitude is halved from 1 to 1/2, this is equal to a minus 6 dB change. In order to have a 10 dB change, this is equal to a multiplier of about 3.16 of amplitude change. And for a 10 times pressure amplitude change, that is a plus 20 dB change. So it's important to recognize these entries here, 1/2 and 2, and the corresponding minus and plus 6 dB changes in SPL. If the pressure amplitude changes by 1/2 for spherical waves, This is equal to a doubling of distance. Which I'll show up there. And if the pressure amplitude changes by 2, this is equal to a half of distance change to the source. So when we double our distance to an acoustic source, the SPL should reduce by 6 dB. But if we get half as close to the acoustic source as we originally were, the SPL should increase by 6 decibels. These are very quick ways of approximating SPL change with distance from an acoustic source. So let's put these SPL values back into our tabulated set of representative acoustic pressures. Our threshold of hearing, when 20 micropascals is put into the sound pressure level equation, of course we get out an SPL of dB of 0 dB, since it is equal to the reference pressure in air. Instantaneous hearing loss, which is of course the top limit of what we may ever experience day to day, is around 120 decibels, but it represents 6 orders of magnitude change from the threshold of hearing to the risk of hearing loss. So 6 orders of magnitude from the threshold of hearing to the risk of hearing loss is a 120 decibel change of SPL. So this means that for every order of magnitude, every 10 times change, that's a 20 decibel change in SPL. There's another level metric that's often used in acoustics, and this is sound power level. We found previously that acoustic power is a source characteristic, which means that it doesn't vary based on your measurement location. The sound power level, which is given as capital L subscript capital Greek pi, is equal to 10 log base 10, once again, sound power capital pi divided by some reference power, power sub ref. And power sub ref is 10 to the negative 12 watts. We can relate sound pressure level and sound power level to the following relationship. Sound power level is equal to sound pressure level plus 20 log 10 multiplied by the radial distance to the measurement location plus 11. So even though the sound power level is a source characteristic and should be independent of the radial location R, when we substitute in these relationships for sound pressure level and the 20 log 10 R, they cancel each other out so that L pi is independent of R. Since the roles from the R in the radial distance R in sound pressure levels, SPL, and in 20 log R cancel each other out. Acoustic intensity also has a level metric called the acoustic intensity level, but it's rarely used. Most often, acoustic intensity is just reported directly. In medical applications of ultrasound, watts per centimeter squared is used quite regularly. And for larger engineering applications, such as measurements of turbine jets downstream and in occupational environments, watts per meter squared is readily used as well. So acoustic intensity level is out there, but mostly we'll report acoustic intensity directly. So let's say we're in an environment where there are multiple sound sources. Let's consider that these sources are incoherent. You may recall that this means that they are at different frequencies. Multiple incoherent sound sources at different frequencies, or even broadband would also apply. Let's consider that we have 3 sound sources. How do we find the combination of the total SPL from these 3 individual sound pressure level values? Maybe, for instance, we were able to measure source 1 when source 2 and 3 were not active, and we found source 1 was 48 decibels. And likewise, source 2 we discovered was 50 decibels, and source 3, 51 decibels. We might be immediately led to say that the total SPL is the sum of these values, But if we do that, we'd calculate that the total SPL was 149 decibels, which is much greater than the threshold of pain. And each of these SPL values individually are around quiet conversational levels. So what's the correct way to combine sound pressure levels? The correct way is to add up the RMS pressures. Specifically, we add up the squared RMS pressures for each of these sound sources, where the RMS pressures are determined by the reference pressure multiplied by 10 to the power SPL divided by 20. When we add up the squared RMS pressures, we take the root of that, and then this total RMS pressure goes into our SPL equation. So let's do that. For the sources, we find that we have 5 millipascals RMS, 6 millipascals RMS, and 7 millipascals RMS. When these are plugged in to this equation for total RMS pressure, and then that is fed back into the SPL equation, we find that the total SPL is just 54 decibels, again in a conversational regime or level. An alternative way to compute this is to directly use the SPL values in the equation that's shown at the bottom right. The total SPL is equal to 10 times the log base 10 of the sum of 10 to the SPL values divided by 10. Sound pressure level is often reported in numbers rounded to the first integer, and let's explore why. So let's say we had recordings that showed us values of decibels of 60.12, 40.48.1, or 77.5721. For instance, we may have done some calculations in our computer or in MATLAB and gotten these numbers out. We would never see this reported in practice. They would instead be reported as 60 decibels, 48 decibels, and 77 decibels. Why is this? This is because fractional or decimal decibels correspond to pressure amplitudes that are near or less than reference pressure. So if we consider a pressure RMS of 0.1 dB, this is in fact equal to the reference pressure change. So all decimal decibels correspond to quantities so small that they are equivalent to absolute changes in your reference pressure, which we cannot practically measure. So as a result, we report all SPL values rounded to integer quantities, and we avoid decimal decibels. So let's summarize what we've learned. Day-to-day acoustic pressures range in amplitude over many orders of magnitude, so we use the sound pressure level, SPL, to provide a helpful means to compare these relative sound levels over a logarithmic scale. Sound power level is also used to quantify sound sources, and when we need to combine decibels, we require summing the RMS quantities before taking the logarithm in the SPL equation. Finally, let's round our SPL values, because using decimal decibels, these are quantities so small that they cannot be measured.
That's it for this video. In the next video, we'll learn about a characteristic of waves that determines how acoustic energy transfers.